Voyager 1 has just shattered the cosmic silence by making contact with a civilization far beyond the reach of our imagination, tucked away in the boundless void of space. Voyager's signal was picked up by an unimaginably advanced alien species whose presence defies all our assumptions about life on planets other than our pale blue dot. This extraordinary meeting opens a new chapter in our journey across the universe. As the world grapples with the shockwaves of this revelation, the age-old questions that have haunted humanity since the dawn of time echo louder than ever. Are we ready to confront the mysteries that lie beyond the stars, and in our quest for understanding, will we find enlightenment or unleash forces beyond our control? Join us as we explore how Voyager 1 just made contact with highly advanced alien species in space. No one could have predicted 47 years ago that the Voyager 1 spacecraft would continue to play a pivotal role in our solar system's exploration of the outer planets. Even after all this time, the probe is still sending data about its travels back to Earth, so it must be doing something right. The communication from Voyager ushers in an uncertain but potentially rewarding future. The Voyager missions took advantage of a special alignment of the outer planets that happens just once every 176 years. This alignment allows spacecraft to gravitationally slingshot from one planet to the next, making the most efficient use of their limited fuel. Spacecraft from NASA were initially intended to travel beyond Pluto, Saturn, and Jupiter, while other probes were to travel past Uranus and Neptune. Even though NASA had to cut back on its intentions because of budget constraints, the two Voyager spacecraft it launched were nevertheless quite useful. As Voyager 2 soared beyond Jupiter and Saturn, it also passed Uranus and Neptune, whereas Voyager 1 was laser-focused on those two planets. 2 golden records were approved to be installed on board the Voyagers by NASA, who recognized that the spacecraft would eventually go to interstellar space. Sounds ranging from whale calls to the music of Chuck Berry were placed on board, as well as spoken greetings in 55 languages in case aliens ever happened upon the spacecraft and were curious about their origins. The 12-inch wide gold-plated copper discs also had schematics illustrating how to operate them and the Sun's location relative to nearby pulsars, a sort of neutron star. A trio of radioisotope thermoelectric generators, which transform the thermal energy emitted by plutonium's radioactive disintegration into usable electricity, power the two spacecraft. A magnetometer, a 2-camera imaging system, various spectrometers, and equipment to detect low-energy charged particles and high-energy cosmic rays were among the 10 scientific instruments attached to the probes. There have been a total of 11 scientific investigations conducted aboard each Voyager by using the communication system to learn more about the planets and moons. Voyager 1's rocket nearly ran out of fuel during launch on September 5, 1977, and the spacecraft nearly never lifted off. However, after a risk-free launch, the probe sped past its twin and went beyond the main asteroid belt between Jupiter and Mars before Voyager 2 could catch up. At a distance of 165 million miles from Earth, the Voyager 1 spacecraft transmitted its initial images of Jupiter to Earth in April 1978. In March 1979, Voyager 1 surprised NASA by detecting a tiny ring encircling the massive planet. Phoebe and Métis, 2 other moons, were also discovered. The large Galilean moons of Jupiter, Io, Europa, Ganymede, and Callisto, and Amalthea were also captured in great detail by Voyager 1. In the same vein as its predecessor, the Pioneer spacecraft, Voyager 2 found that the moons of Jupiter were dynamic, independent worlds. Intriguing new information regarding these naturally occurring satellites was also uncovered by Voyager 1. For example, the fact that Io is modeled with yellow, brown, and orange and has numerous volcanoes demonstrates that moons, similar to planets, can have dynamic interiors. In addition, images of Europa returned by Voyager 1 revealed a mostly flat surface with lines running across it, suggesting the presence of ice and possibly an ocean beneath it. A large subterranean ocean of liquid water, possibly capable of supporting life similar to that on Earth, is probably harbored by Europa according to subsequent observations and analyses. On March 5, 1979, Voyager 1 approached Jupiter within 174,000 miles, passing near the tumultuous cloud tops. The probe's next target was Saturn. The only year that scientists had to wait to capture close-up images of Saturn was 1980. Surprisingly, the ringed planet was just as full of surprises as Jupiter. One of Voyager 1's targets was the F ring, a thin structure discovered only the year previously by NASA's Pioneer 11 probe. Voyager's higher-resolution camera spotted two new moons, Prometheus and Pandora, whose orbits keep the icy material in the F ring in a defined orbit. It also discovered Atlas in a new ring, the G ring, and took images of several other Saturn moons. Voyager 1's primary mission came to a close with the Saturn encounter. Following that, attention turned to keeping tabs on the spacecraft as it raced toward interstellar space. Weighing 1,590 pounds, Voyager 1 captured one of the most famous images in spaceflight history 20 years before it achieved that feat on February 14, 1990. The probe turned back toward Earth and snapped an image of its home planet from 3.7 billion miles away. The photo shows Earth as a tiny dot suspended in a ray of sunlight. The pale blue dot photograph stands out among the hundreds of other images taken that day by Voyager 1, which included the Sun and 5 other planets in a multi-image solar system family portrait. This serves as a constant reminder that Earth is a tiny dot in an infinitely huge and unfathomably massive universe. In August 2012, Voyager 1 sprung loose into interstellar space, leaving behind the heliosphere, the enormous bubble of charged particles that the Sun blows around itself. The results came to light after a powerful solar eruption was recorded by Voyager 1's plasma wave instrument between April 9 and May 22, 2013. The eruption caused electrons near Voyager 1 to vibrate from the oscillations. Researchers discovered that Voyager 1's surroundings had a higher density than what is found just inside the heliosphere. It seems contradictory that electron density is higher in interstellar space than it is in the Sun's neighborhood. However, researchers explain that at the edge of the heliosphere, the electron density is dramatically low compared with locations near Earth. After retracing their steps through Voyager 1's records, scientists finally settled on August 25, 2012, as the formal departure date. The electron oscillations and the spacecraft's readings of charged solar particles both contributed to fixing the date. On that fateful day, which coincided with the death of Apollo 11 astronaut Neil Armstrong, the spacecraft detected an increase of 9% in galactic cosmic rays, which originate from beyond our solar system, and a one-fold decrease in these particles. At that point, Voyager 1 was 11.25 billion miles from the Sun. Voyager 1 has been sending back a wealth of useful information about the interstellar medium ever since it soared into orbit. Among its many findings are proof of the extremely high levels of cosmic radiation and evidence of the interaction between charged particles generated by stars and those originating from the Sun. Engineers are still in awe of the spacecraft's capabilities. For instance, in December 2017, NASA declared that Voyager 1 had effectively oriented itself to talk to Earth using its backup thrusters. The last time the trajectory correction maneuver thrusters were activated was during the flyby of Saturn in November 1980 by Voyager 1. From that point on, the spacecraft's usual attitude control thrusters became the primary means of guiding it into an optimal communication position with Earth. However, as the attitude control thrusters started to fail, NASA opted to try out the trajectory correction maneuver thrusters, which could let Voyager 1 last longer in operation. In the end, that test was successful. There are further steps that the mission crew has taken to increase Voyager 1's lifespan. To assist in preserving Voyager 1's limited power supply, for instance, the cameras on board were disabled not long after the pale blue dot photo was captured, since the cameras couldn't capture much light in space. 5 additional scientific instruments have been disabled by the mission team. At the same time, Voyager 1 stopped transmitting any data to Earth in November of last year, suggesting that it was not collecting any engineering or scientific information. Fixing the fault of the universe's most isolated spacecraft isn't as easy as pie. Problems arose for NASA when the probe suddenly stopped relaying data on the stuff between the stars. Commands transmitted from mission controllers take 22.5 hours to reach the small probe, and the engineering crew must wait the same period again for a response. The spacecraft is 15 billion miles away and hurtling along at 32,000 miles per hour. More than 5 months have passed as NASA has worked on the matter. In March, the initial intention was to offer the spacecraft a digital poke. This method is analogous to a doctor using air puffs to identify cavities in teeth. The NASA team sent a command to the spacecraft telling it to relay a full memory readout back to Earth, emphasizing any malfunctioning components. The Flight Data Subsystem, one of Voyager's 3 onboard computers, is in charge of packaging the science and engineering data before returning it to Earth. This chip is where the reported malfunction was discovered. Because of the bug, the computer was producing repeating gibberish consisting of binary ones and zeros, giving the impression that it was stuck rather than providing science, temperature, and engineering data. Since NASA had to become creative because the broken chip couldn't be replaced, they had to find a different space in the Flight Data Subsystem memory to store the troublesome code. The scenario became much more complicated because no single site could carry the entire section of the code. So, they devised a plan to keep in touch and work together while dividing the affected code into smaller pieces and moving those pieces into the computer's memory. Now, the Jet Propulsion Laboratory of NASA has officially declared that Voyager is back in service following the most remarkable long-range software update in history. We now eagerly await the influx of Voyager 1 scientific data in the upcoming weeks. It is unclear what caused the chip to malfunction, but the team is considering the possibility that it was damaged by an energetic particle from space or just became worn out after 47 years. It's also unclear to NASA if this is a solar or interstellar occurrence. Voyager 1's next big encounter will take place in 40,000 years when the probe comes within 1.7 light-years of the star AC plus 79 3888 or Gliese 445. Instead of sending Voyager 1 to Proxima Centauri, which is 4.22 light-years away, why did we direct it toward Gliese 445, which is 17.58 light-years away from Earth? No effort was made to direct Voyager 1 towards objects beyond the solar system after passing Saturn and Titan. Not even a preliminary attempt to conduct scientific research was considered. The whole history of Voyager 1's operations since 1980 can be attributed to an extended mission that was developed after the initial mission's completion. The remaining systems on Voyager 1 and 2 will enter a safe mode when the power level drops below what is required in approximately 5 to 6 more years. At that point, the computers will detect a power situation. Only the 60 bps engineering feed will make it back to Earth. The signal will be lost, and Voyager will lose alignment of the high-gain transmitter to Earth if the computers are not operating and if ongoing guidance is not provided. The computer will turn off completely a few years later when the instrument bay heaters fall below a certain critical level. The Voyager will essentially cease to exist. The craft will reach space temperature after another 800 years when the plutonium RTG cores will have reduced their heat output to less than 1% of its initial output. About 39 millennia after that, Voyager 1 will pass an unimpressive 1.76 light-years from Gliese 445. This is not because Voyager is traveling towards Gliese, but because Gliese is screaming towards the solar system at 12 times the velocity of Voyager. It will actually pass the Sun with over 2.5 light-years distance to spare. So, no special cause for alarm. While Voyager will be only about 2 light-years away from Earth at that point in time, as Proxima approaches its closest proximity to the Sun, it will begin to move away from us again in around 10,000 years, making the journey nearly 30,000 years longer. Even if it weren't, then crossing the 4.22 light-years would take Voyager close to 90,000 years at its current rate of travel. So actually, totally by accident, scientists chose the star that will provide the earliest closest encounter available in the next 100,000 years or so. Not that it will make any difference by then, Voyager 1 will be just a lump of inert metal and plastic serenely tumbling through the inky darkness, all alone in a shining sea of stars. Humanity's most distant and first emissary to the Milky Way. Is there anybody out there? Because of its scope, SETI is an undertaking that calls for substantial teamwork. For instance, the 100-meter Green Bank Telescope in West Virginia, the largest steerable radio telescope in the world, is being used in a project that is being supported by the Planetary Society to search across a broad spectrum of radio frequencies. While the radio telescope's wide field of view allows them to detect tens of thousands of extra stars and planetary systems, their observations center on 100 stars known to have planets orbiting them. The next step is for citizen scientists all over the globe to filter through the data and identify the most promising signals by classifying them. This will assist in identifying the various sources of radio signals that Earth's intelligent life has produced. At last, trained SETI specialists go back over those signals to see whether they still hold any water as possible indicators of intelligent life. It all adds up to hundreds of hours of work for what amounts to a search for a small fraction of space. Perhaps we haven't found what we're searching for because SETI's reach is very huge. Given the size of the universe, probably any extraterrestrial intelligence is likewise running its own SETI program. We have the same chance of being detected by a highly developed civilization as they have of being detected by us. The signals we intentionally put out for this reason have the best chance of being picked up by other types of life. Even while all electromagnetic communication travels at the speed of light, not all signals are equally strong as they recede from their origin. Several parameters, such as the transmitter's power and the signal's frequency, determine the maximum distance a transmission may cover. Even though it's a popular science fiction concept, it's quite unlikely that extraterrestrials will be able to pick up our wayward television signals. Since television signals aren't meant to go very far, the transmitters used to transmit them are rather feeble. By this point, the first television transmissions have probably made it beyond our solar system. However, by the time they reach interstellar space, they are so faint that they would be nearly impossible to tell apart from the vastness of the universe. The range of some of our radar signals is probably going to be quite large. Similar to the now-defunct Arecibo Observatory, which utilized radar to detect faraway asteroids and other celestial bodies, missile detection radar makes use of extremely powerful transmitters. If the extraterrestrials weren't much further away than the nearest nearby star system, it's plausible that they might detect those radar emissions and determine that they were technological in nature. To be picked up by alien civilizations, humans have purposefully transmitted multiple powerful signals into space. The act of intentionally transmitting messages into space has sparked discussions within scientific and ethical circles. One worry is that our entire species and planet are entrusted to a tiny handful of people or even just a few individuals. A number of ethicists have voiced concerns about the inherent unfairness of this. Another problem with METI is that it's hard to predict what kind of aliens could be listening to our signals and what they could be trying to accomplish. There is a chance that we could be discovered by an advanced alien race that is either trying to conquer the galaxy and wipe out all life on Earth, or by a more benign race that is interested in sharing knowledge about interstellar travel, power generation, or any other technology that could change the world. Experts in space policy have argued that it is not sensible to put resources on METI since we do not know what would happen if we established contact with intelligent aliens. Ultimately, though, it's possible that we'll be discovered by aliens looking for life beyond their own planet, whether we try or not. The possibility of life's existence elsewhere in the universe is one of the fundamental and unanswered mysteries about our reality, and it may not be up to us whether we solve that mystery. Thanks for watching another episode. While you're still here, make sure to click the video on your screen for more mind-blowing videos about space.